Alright, welcome to the first in a series of videos designed to help summarize a lot of the important concepts we discuss in class. A lot of times things go quickly in 43 minutes, and we need to make sure that we are getting the information that is most important about the lessons. That's why it's important to review videos such as these and make sure that you've acquired all the necessary information. Also, feel free to pause, rewind, and do whatever you need to do to get the content. You don't have to watch it all in real time. Take your time ingesting the information. Now, we went over a couple of IB-style questions regarding quadratic functions, and the actual getting of the answers is really straightforward, but I want to discuss two things. The first is good ways of communicating how you got your results and communicating that you understand, not just know how to get the answer. Then the second thing is using technology for homework, specifically Desmos, as a way of making sure that we're doing this work correctly. So I'm going to first also point out the command term write down. When IB uses write down, it means that the information given in the figure and the text is enough information for you to be able to ascertain what they want you to do. In other words, no calculations necessary. So identify P and Q. In IB world, that's enough to get your mark. You'll probably get 1 point for that, maybe 2. But you have to make sure that we're checking our negative and our positive, that we did that correctly according to this particular formula. It says here the opposite of P and the opposite of Q, which means my function would have to be x plus 1/2 and x minus 2. I just want to verify that this is doing what it's supposed to, which I know it will when x is 2, 2 minus 2 is 0, so we're going to zero out the function for sure. But just to verify to the reader, by substituting 2 in for x, I do in fact get 0, so I know I did this correctly. The second part of the problem is to it says the function has a minimum value in the point C. Find just the x-coordinate of point C. So all we're really looking for is the axis of symmetry. And you'll notice what I did here. I added the two x-intercepts and divided by 2. That's the midpoint formula, which gives you on the number line the exact middle point between the two data points on the number line. You should also notice that this is the same thing as the concept of average. To average, you add two numbers together and divide by 2. The average of two numbers is literally the midpoint on a number line. So, in this case, it didn't ask me how to find the x-coordinate of C, so I'm going to use the most elegant and efficient method possible. There is another way, of course. Oh, before I do that, sorry. Before I do that, I do want to point out that I didn't just get the answer. Now I'm going to go up to the graph and write down a little bit of a note to verify this is absolutely correct. So I'm looking at 3/4 and finding the distance from 3/4 to 2 is 1 1/4. And when I look at the distance from 3/4 to negative 2/4, that's negative 5/4 away, or 1 1/4. So in other words, I verified graphically that 3/4 is in fact the midpoint between negative 1/2 and 2. Anyway, method 2 is a traditional approach, and that would involve foiling the function to put it in a standard form, and then using the equation for the axis of symmetry, the opposite of b over 2a, and that gives me 3/4. Should be no surprise, of course. So, the piece about the writing, first of all, I forgot, there is a third method, which would involve using calculus, which is basically using a nuclear bomb to take out an anthill. In this case, this is so much more efficient than using calculus to answer the same question. It would be absurd to use that other method, so I'm not even going to show you. Plus, we haven't started calculus yet. Anyway, the other thing we need to do is to verify our work using technology. And this is not always necessary just to verify that you have a right answer. This is also an opportunity to practice using technology. So I'll show you the two things I did, and it's really quite simple. I put in the function as given, the x plus 1/2 and the x minus 2, and it graphed the parabola. And then I verified that the parabola is at negative 1/2 and 2 as x-intercepts, and I could also see here that 3/4 is in fact the x point of C, the minimum point on the graph. I also have this point here, 0, negative 1, and what 0, negative 1 does for me is it verifies my foiled form. I foiled this out to get it in standard form, and now I see that these two forms are the same. Notice here, this is a blue and this is a red, and the graph shows up purple because basically we're seeing both graphs. Actually, that does look more blue. There was another one that was purple. Never mind. Anyway, all you have to do is type in all the work that you've done, and you will have Desmos representing all of the solutions, a whole solution set to the problem, or to the equation, sorry. The next piece that we looked at involved inverses, and it required us to jog our memory. So I want to take this into a discussion of exponential and logarithmic functions, but first let's explore the inverse in the quadratic form. Now, the part of the problem that was straightforward algebra stuff is the act of completing the square. Now, I completed the square here by taking out the 13 and substituting in a value that I like better. I take half of -6, which is 3, and square it, and I get 9. But I have just altered the balance, so I take away 9 out here so that these things balance out and the equation still retains its same value. Now I'll sequester the first 3 terms and factor, and I find, of course, by design they have 2 of the same factors, and 13 minus 9 is 4. Now you can achieve the same result just by using the equation for the axis of symmetry, x equals the opposite of b over 2a. Then you substitute that number, that'll be 3, and then you find f of 3, that'll give you 4, and you'll know -3, 4 represents your a and b values, or 3, 4 represent your a, b values. Now, it's important not just to do the algebra, but to make sure we know what's actually happening. And so we're looking at a parabola who's supposed to be only when x is 3 or greater. So I'm going basically from the vertex and then to the right. The other thing to remember is a parabola can be transformed using shifting. So I shift the parabola y equals x squared right 3 and up 4. And so I get this graph. Oh, by the way, this is me verifying my work. I did and the opposite of b over 2a, I got 3, which matches this one right here. And then I could take 3, put it into my equation that was given, and verify that that's going to give me the result 4, which it does. Now, what I did is I produced a graph, and I knew it was going to be a parabola, so I just simply shifted the parabola to the right 3 and then up 4, and then I drew this part. I drew the dotted part in here just to show you the rest of the parabola, but this part of the parabola is not part of this particular problem, because again, I have to pay attention to the domain restriction at the very beginning. Now I have to find the inverse function. First thing I did actually is I looked at the graph, and the graph shows a parabola that has a vertex at 3, 4. So if I was going to invert that, I just switched the x and y, and now I'm going to have a starting point for my inverse at 4, 3. And then instead of increasing upward like a parabola does, we're going to increase downward curved like a square root. So I identify that the inverse of a square is a square root. I can ascertain the equation simply by using common sense. That is to say, it's probably going to be the square root of x minus 4 plus 3, because we're going to go right 4 and up 3 to make our square root graph go. But here's the algebraic way to verify that result. So here we're going to have x equals y minus 3 squared plus 4, which is literally the inverse of y equals x minus 3 squared plus 4. So right here, this actually is the inverse function, but we're going to make it look nicer by solving for y so we can get it in the correct order. So the first thing I do is I subtract 4 from both sides, and then I take the square root of both sides, remembering the plus or minus, and then I add 3 to both sides. But to make the f of x a function, we need to not have plus or minus. We need the one that's going to be the exact inverse here. I choose the positive one because that will add numbers to 3. So here we start at 3 and we add numbers to it, and off we go. So the domain of this function is any x greater than 4. Notice this notation, x is an element of any number from 4 to infinity, including 4, and then not including infinity because that's not a number. Now here again, I want to talk about how Desmos can really help clarify or crystallize a lot of this work. Hold on a second. There. So, I'm going to look over here and see the functions that I've entered. I actually have 3 functions entered in, and I have a couple of tables, and I also drew the line y equals x and dotted it for your benefit. You'll see the 2 graphs do appear to be mirror reflections over that line y equals x, and recall again what we're doing is verifying that I've found the inverse. So, first thing I want to show you is that the parabola only graphed from 3 or greater. I use this notation, these rounded or these elephant ear brackets, with x greater than or equal to 3, and that tells Desmos to only graph in that domain. So this part right here is part of the parabola, but it's not showing up because I restricted the domain in Desmos. The other thing is, this is where that purple thing was happening. This is purple, and this is blue and red, showing us that these two graphs are in fact overlapping. And so this was the given form of the equation, and this is what I did by completing the square. Now I have verification that I completed the square correctly. Finally, then we also have Finally have the issue, is my answer for the inverse indeed the inverse? And you'll notice what I did is I made a table of values with the function f of x, and I made a table of values with the function g of x, and we can see here that each of the points 3, 4, and 4, 3 are literally inverted. 5, 8 becomes 8, 5. So let's look at the inverse for a second. What we should understand about inverses undo one another. They're operations that will do the opposite of their partner. So squaring is an inverse operation from square rooting. But also, subtracting 3 and adding 3 are inverse operations, and subtracting 4 and adding 4 are inverse operations as well. When you apply inverses, you literally undo the work that the function did. So if I put in 3, I get out 4. The inverse says, we'll take that 4 and give it back as a 3. I put in 5 and I get 8. The inverse says, well, I'm going to take that 8 and give you back your 5. So when we do behave that way as a function, and we invert a function, we are going to get a graph that is literally reflected over the line y equals x. All inverses behave that way. So let's look at other inverses. This is one of the most important inverses we're going to get. First of all, this function is the exponential function, y equals e to the x. We use base e in calculus for reasons that will become clear this year. But I want to show you what Desmos can do. Desmos graphed the inverse, even though I didn't know what the inverse of this function is. So understand, of course, we're going to be talking about inverses as they relate to exponential functions. Sorry, bear with me, getting used to the technology again this year. That's all the way to the end of that. Okay, so anyway, I don't have to know what the inverse is in order to be able to graph the inverse. The blue graph is in fact the inverse of the red graph. We can see it visually, and we could also see that these points appear to be inverted. But I don't know the equation for the inverse yet. Now, exploring the exponential function, we need to understand what our inputs are. Inputs are the same as the independent variables. It's what we start with. And in this function, we are going to input exponents on e. -2 is an exponent on e, -1, 0, those are all exponents on e. Notice that when x equals 0, y equals 1, because e to the 0 equals 1. Anyway, if I look at the outputs are the dependent variable. Those are going to be powers of e. So on the graph we can see each of these y values is a power of e. This is not 7.389, it's actually e squared. This is not 0.135, it's actually e to the -2. And here's e to the 0 and e to the 1 and so on. So we put in exponents, we get out powers of e. This is inverting, so we are going to put in powers of e and put out exponents. So what I did was I just basically took the powers of e, like e to the -2, e to the -1, and so forth, and then I used this natural log of x sub 2, which gives me all the natural logs, which is essentially all of the exponents. So here's what I learned. The natural log is what we call the inverse of an exponential function. We don't like to write our inverse functions this way because they're not solved for y. In order to solve for y, we had to invent a language. So the language we use to invent inverse of exponential is natural log. So to see how that works, understand that these are inverses. This time I put in powers of e and I get out the exponent itself. Here, for example, the natural log of e to the -2 is -2. I put in e to the -2. The natural log says, just give me the exponent. Forget about the outcome. Same thing here. I put in e squared. I get out 2. So what do we need to know about logarithms? Logarithms are just basically a way to extract exponents from powers. Logarithms are also inverted exponential growth curves, or decay. We'll look into that later. If I understand how exponential growth behaves, all I have to do is invert it, and I understand how logarithms behave. For example, exponential functions are never negative. Logarithmic inputs, you can never put a negative number into a log. See, there's no graph over here. Exponential functions have an asymptote with the x-axis. Logarithmic functions, asymptote with the y-axis. Other patterns are things that you can observe, but you can pause this and study the video, or go on to Desmos and check it out yourself. But I hope that clarifies some things about inverses, and also how to use Desmos, and also how to make sure that we write our work well so we can understand what we're trying to say, and how to check our answers. That's a lot of stuff in one video. Make sure you take it all in. Have a great day.